In this video, we will try to get the magnetic field due to a current carrying solenoid. So solenoid is nothing but we have a long current carrying conductor that is bound in the form of a spring. So this is solenoid where current enters at one place and through one side and through other side current leaves out. So you can consider it as n number of current carrying circular loop placed one after another. Okay. Now see this is a current carrying loop. Okay. Now with respect to one loop, we know how to get, let's say the current is passing in this direction. Now how to get the value of magnetic field at the top position? Here, in this way, in this way, in this way. So here, if the current is passing in this direction, now magnetic field will be circular around the loop. I will use red color marker. So it is circle. Here also it will be circle. Here also magnetic field is a circle around it. Okay, now see one thing. Here the direction is inward. Here inward. See the two nearby coils. With respect to this coil, it is with respect to this coil, okay. The direction of magnetic field here will be at this point will be downward. See, current carrying downward. But here with respect to this coil at the same point, so I am talking about point P. At point P, with first coil gives a magnetic field in this direction downward, but the second coil gives in upward direction. These two magnetic field will cancel, which means in between the coil there is no magnetic field. Now what will happen? This coil goes in this way, next to. So this is the magnetic field around each coil. So see one thing, first magnetic field lines, second, third. See one thing, magnetic fields are summing up along the direction of the axis. See, 1, 2, 3, 4 in this way, magnetic field will go. That will be along the axis. Just take the magnetic field, direction of magnetic field with right hand thumb rule. Okay. So direction of magnetic field is this. This we have proved. Now come back to this. I mean, ignore the red colored mark. That is just direction. We want to find the magnetic field due to a circular loop at different positions. One is at this position, at this position, at this position, at this position. At this position, it is 0. We have proved. Okay, so magnetic field lines will be going in this way. Okay, from north to south. This one is north, south. North to south. On the top, here the magnetic field is 0, which is very far away from the solenoid. Okay, so we have magnetic field here. Here also we have magnetic field, but the direction of magnetic field is in this direction. Now I am going to consider an ambient loop here. First thing we will check, is it an ambient loop? First condition, there should be current passing through the ambient loop. Now see, this is the loop we are considering. For example, now we have a current carrying conductor. So when the moment I am placing a current carrying circular loop, see this current is passing through the loop, right? Into the loop, through the loop, through the loop, through the loop, through the loop. So current is passing through the loop. First condition is satisfied. Next one is B should be parallel to the tangent or B should be perpendicular to the tangent. So here in this case, this is the tangent, direction of loop, right? Direction of loop and B should be parallel. Here in this case, it is parallel. But what is the case here? Here B and the loop is perpendicular. So that is also fine. Here what happens? Third case, B vanishes. B is 0. So all the cases are there. Here. So I will take A, B, C, D. So AB, B is parallel to the loop. In BC, B is perpendicular to the loop. And in CD, B vanishes. All the conditions are there. So this is ambient loop. Okay. Now, how can I consider the ambient circular theorem? Closed integral of B dot dl is equal to mu 0 into. What is the total current passing through this? We have 1 coil, 2 coil, 3 coil, 4 coil, 5 coil. Let's say we have considered, if we are considering the whole solenoid, how many coils are there? So many. Let's say I have, these are the 3 coils from the solenoid. So I passes, I passes, I passes, I passes. So how many I's are there? 4 I's. So if N is the total number of coils and if current through each coil is I, then total Ni current passes through everything that will be passing. Okay. So I have taken a small portion here, H. So I need to find what is the total current passing through this H, this element. Okay. So for that, I am going to define a new quantity called as number density. Number density is nothing but number of turns per unit length. Now per unit length, small n number of turns are there. Now with H length, how many turns will be there? H into N. So total turns in H length, total turns in H length is equal to N into H. So total current entering the loop is if N into H conductors are there, then N into H into I. That is the total current entering. Okay, so here mu0 into total current is N into H into I. Clear? Now, see, this is the total loop, right? From A to B, then to C, then to D, then to A. So I am going to split into 4 because magnetic field at these points are different values. So I can't do an integration. I will consider in between A to B, then B to C, then C to D, then from D to A. So this thing from A to A, closed loop has been split as, I will mark it here. So integral A to B, B dot dl, first case, then from B to C, B dot dl, then from C to D, B dot dl, then from D to A, B dot dl is equal to this value, mu0 n h I. So this is so after this step, you should bring this step. Because we are doing the total enclosed path, we are going to split as 4 paths and add it. It's the same. Why I have done in this way, we know that here B and loop is in the same direction. So here B dot dl is nothing but in the first case B I can take outside and total length of AB is nothing but integral of dl, that is H itself. Total length here is H. What is the value of this one? In the next case, see here loop is in this direction, magnetic field is in this direction, 90 is the angle. So dot product is nothing but d dl cos 90. Cos 90 is 0. So this will become 0 here. Okay. Now CD. CD is a point where magnetic field is not there. So 0 into any value will be 0. So that is also 0. So C to D we got the value of B dot dl as 0. The reason was C to D magnetic field is 0. Now from D to A, B dot dl, D to A. So here in this here we have magnetic field, but length dl element is perpendicular to the direction of magnetic field. So this one is 0. So in the examination you have to explain the reason in between BC. Why? See, this is BBC, right? Magnetic field in BC. This one is BAB. Magnetic field in AB. This is BCD. This is BAB. So out of this, only magnetic field in CD is 0. So reason for these two to be 0 is nothing but the dot product became 0. Okay. Now we have only this one. This one is BAB. BAB in the H. So we can find the value of magnetic field along the direction of AB. That is BAB in the X. This one is equal to mu0 into NXI. Next step, BAB into H is equal to mu0 NXI. X can be cancelled. So BAB is equal to mu0 NI. What is N here? N is number density. So not number density, number of turns per unit length. N is equal to capital N divided by. So this is the magnetic field due to a solenoid along the center. And what we have seen is here magnetic field is 0. So why we are using magnetic solenoid? To give an intense magnetic field, and that too in one direction. See, what we have seen from this is, when we have a solenoid here, if we are keeping it as conductor, then the magnetic field is, directed circular around the coil. But when we are keeping the coil in the form of, circular along the across the loop. But when we are keeping the same current carrying conductor in the form of solenoid, we are getting magnetic field, an intense magnetic field. The value is mu0 and I, and that is unidirectional. So here the direction of magnetic field is this. So after some time that will bend and goes in this direction. So in front of this we have an intense magnetic field and directed in one direction.